Welcome to our discussion on air. I want to talk to you about, pneumatics, specifically how we take air and apply air and make things go and how we control it, and we're going to talk about the principles of air and the properties of air, and more specifically the properties of compressed air, and actually maybe different kinds of air, if there are different kinds of air. And actually there are, or at least as far as pneumatics are concerned, there are different kind of physics to the air and properties that we have to discuss. So let's move on and let's talk about this. So welcome to lecture 1, properties of air and pneumatic fundamentals. And we'll move on here and we're going to talk about pneumatic examples. So now I think you guys know what pneumatics is, but essentially what we're doing is we're taking air and we're making it do work for us. It's actually kind of like a mechanical system. Although as opposed to making things move like shafts or pulleys or gears or things spinning, we're actually making air flow. So there's a dynamic involved in this. And actually there's a cool word we'll stumble across. It's pneumodynamics. But for now, let's just talk about what we use it for. Well, it's used everywhere. Like it's huge in all different kinds of automation industries. It's used all over the place. I mean, you've seen that show, How It's Made. Well, how are all of these things moving that go up and down and around and stuff? Well, a lot of those things use pneumatic actuators. Linear actuators go in and out, back and forth with pressurized air. And also there are pneumatic motors that spin. Let's just take a look at some of this industry. So manufacturing, huge. Metal forming, plastics, metal handling, assembly, stamping, anything that moves and needs some kind of force. That's huge in manufacturing. Transportation? Oh, absolutely. And all kinds of things. Actually, a really good example is if you get on the subway and the doors that open and close, they actually use pneumatic actuators to open and close. I'm not sure if you've ever got stuck in the door, but if you actually get stuck in the door, it'll kind of stop. I think nowadays they pop back out. Actually, I'm talking about subways when I used to ride the subway, which was 20 years ago. So it could be that the new subway doors actually use motors to go back and forth. But I mean, if you wanted to kind of clamp onto something, you can use air because air is very forgivable. I remember getting stuck in the door in the subway as it closed, and it just closed and just kept pushing. I think nowadays they turn around and open again. But I remember the train wouldn't move until, if anyone was stuck in there, it wouldn't move until the door actually closed. But the thing that closed them were these pneumatic actuators. And I remember when they were moving, you could hear a little bit of you could hear the air. Transportation, it's all over the place. Home improvements, essentially what's going on is that anywhere we're dealing with opening and closing and moving things, it's a really big deal. So to improve environmentals such as compacting waste materials and floodgates and rivers and dams, essentially anything that's going to move one way or the other. What I was thinking about when I said home improvements was I was thinking about air nailer, but that's actually down on the bottom as well in the construction. So essentially in construction auto repair, air nailers are used. You might have heard them or seen them or even used them where they're applying nails with this air going. It makes that noise. Yeah, I do that good because I've done it many times before. Make that air noise. So anywhere where we need to apply force, we use pneumatics. And they're just all over in huge kind of industries. Medical industry, it's a huge thing in medical industry. Prosthetics, physiotherapy devices, surgical industries, the dentistry industry. I think you know that. I mean, those are when they're in there, right? That's actually a thing that runs on air. Now, you may not know that, but it's pretty cool that it does run on air, actually. And, I would rather not have an electric motor in my mouth. I'd rather just have some kind of thing that's running on air in my mouth. It's pretty cool. So we're going to talk about the mechanical transmission of power in a little bit. But pneumatics has a really special kind of attribute about the mechanical transmission of power. We'll talk about the cool things in a little bit. When we have precious environments, like situations like where we're packaging food or special chemicals, or where we don't want an environment where we're going to add grease or maybe even electric shocks. We don't want to use electricity. We don't want to use anything that's got grease or any kind of motor or anything needs a bearing. Well, a lot of things need bearings, whether they have pneumatics or not. But often for purity, we use pneumatic systems for packaging any kind of special materials like food and or chemicals or pharmaceuticals, stuff like that. So we will, as we go on, you'll start to really realize how cool air is and how unique pneumatic actuators are, and why we can use them in certain places where we may not use other ones. For instance, I remember years ago, way back when we got the compressor out, we were at the cottage and we were drilling holes through the beams under the water at the cottage. And I went down there with an actual drill that ran on air. Yeah, we had the compressor up on the shore. Well, I didn't want to run an electric drill, under the water, especially one that plugged in the wall. But air, no problem. It worked, and all we had to do is kind of re-oil it, and then it just continued to work just fine. So there's an environment underwater where we can use air. Pretty cool. So what's going on is that I need to get in a little bit of the physics of how all of this works and stuff, and we'll talk about gases and the dynamics. There's the physics word that's kind of popping into this. And yeah, we will actually be studying physics. The physics of air as we go on through this entire course. So we know what a solid is. It got really strong interactive forces. So those molecules are like bound together. They're stuck together. Now, when we get into liquids, those molecules are also a lot closer together, but a little bit of a weaker interaction. What happens is when we get kind of beyond the fluid into the gaseous state, what happens is those van der Waals forces break down. Some of you guys may know what that is. Don't worry, I'm not going to quiz you on what that means. But essentially, it's the molecular kind of forces between the molecules. Because the gases are out and floating around, the molecules are out and floating around, they kind of have different physical properties to them. And actually, they have a whole different kind of rules or laws of physics that we apply to the molecules in a gas than we would the molecules in a liquid and or in a solid. The physics kind of changes a bit, and we have certain properties that we can look at are specific to a gas that are much different than, say, the properties of a liquid. So let's just continue on here. We're going to define a gas a little bit more. So they're irregular kind of molecules going all over the place, and they're very weak forces that they're not attracted together, and they've got a lot of kinetic energy. They're flying every which way, going all over the place. So there's this active, there's this dynamic. There's a lot of actual kinetic energy in the molecules in a gas, a lot more than in a liquid, and a lot more than in a solid. I think you guys know that, no big deal, but we have to kind of hold on to that concept. Okay, so the thing is, what's happening is that these molecules that are flying every which way, they're going in a single direction until they hit something, and then they hit something, and then they turn around, and they go off in another direction, but they're constantly kind of banging onto things. The cool thing is that when they bang onto something, whether they bang onto some kind of other molecule, but let's just say they bang onto maybe the wall of whatever they're kind of stuck in. Maybe we have like a closed system, and those molecules are hitting the wall. They're going to apply force. Yeah. And depending on how many molecules are hitting over a certain amount of area, we end up with something called pressure, whatever that is. Okay, let's move on. If we take a look at what an ideal gas is, an ideal gas is somewhere kind of beyond the solid that a gas is, and it's actually, let me go back. Let me not even say that. I pretend I didn't say that, although I'll kind of mention that again in a minute. But let's just talk about what an ideal gas is. An ideal gas is a situation where we have a gas and it's in a closed container. If we don't have a closed container, then we can't apply the laws that we've established, that have been established for air. Essentially, like I said, when we were talking about air and gas, the physics, the kind of the rules and the laws and the formulas we use are different than the formulas and laws that we use for liquids and or solids. But the thing is, also those formulas, they don't work unless all of that gas is stuck within a single container. It's enclosed in a container. I mean, to some small degree, we can still use those in, let's say, in a room. Okay, like the room I'm in, like, there's a little air leaking through the door and the window, and the whole place is not hermetically sealed. But the gas laws, I just told you what they were, they still apply to a small degree, but ultimately the air in this room is not an ideal gas. If I were to hermetically seal this room perfectly, then it would be an ideal gas. So when we're talking about an ideal gas, we talk about essentially a gas that is completely closed in some kind of environment. Plus, an ideal gas is one that's not completely compressed, more like a solid. I mean, as you know, if you were to compress a gas enough, it would turn into a liquid. And if you were to compress it even more, it would actually turn into a solid, because as we know, things have this freezing point. Well, even gases have a freezing point. So what I'm saying is, as soon as we go beyond really high pressure, if we pressurize something to an insane amount, squeezing those molecules together, they're interacting more like a liquid, and they kind of leave the ideal gas law. Also, if we have gas that's really hot, kind of like plasma, we step outside the ideal gas, because the definition, I guess we could say, of an ideal gas is an ideal gas is something that we can apply the gas laws to, whatever they are. We're going to definitely delve into the gas laws, but for now, we're just going to say, when we talk about a gas, there are these formulas we can add to it, but it has to be an ideal gas. It can't be really highly compressed, and it also can't be really low, very close to absolute vacuum. Like if we were to go to the exosphere, or way up high in the atmosphere, and we were to study that gas, it's not quite an ideal gas. Again, it's also not in a container. So an ideal gas is pretty much the kind of the gas we're going to be dealing with in compressed systems, in a compressed air line, in an actuator, in a compressor, or a tank or something. So an ideal gas is pretty much like air we use, or it's the gas that we use for pneumatic systems. Okay, so I just needed to say this, that we're going to deal with an ideal gas. As soon as we vent gas out into the atmosphere, we can't really call it an ideal gas, and we can't use the gas laws on it any longer. Just going to have that in mind, and then we can move forward. What we got here is we have the atmosphere. I want to talk about kind of atmosphere and something called atmospheric pressure, which you know about. But let's just step into this. What's actually the atmosphere? Well, essentially there are all these different levels of the atmosphere, right? And weather occurs way down at the bottom. And then as soon as we go above kind of the weather zone, what's going to happen is that out of the troposphere is kind of where the weather still exists. Out of that, then we get into the stratosphere, which is kind of, we think getting closer to space, and as we go higher and higher and higher, and eventually we're kind of out into space. We're into the exosphere. And actually, it's interesting, even if you were to go into space, if you were to go out to the 100-kilometer limit, there's still a little bit of air out there. It's so thin, but it's still called an atmosphere. So there are all these different levels of atmosphere. We're not really going to get into them, but the only thing I need you to kind of get from this is that as we go further and further and further up, the gas gets thinner and thinner. We'll talk about that in the next slide, or in a couple slides, when we actually kind of unpack what atmospheric pressure is. Okay, let's continue on. So now, this is cool. I don't know if you guys knew this or not, but there's actually 78% of the air is nitrogen. Nitrogen's inert. You can breathe it. Actually, obviously, I'm breathing it right now, and so are you. We're all breathing nitrogen. Now, nitrogen's got a little oxygen in it, right? So the oxygen is 21%. I think you guys know that generally the atmosphere has got about 21% oxygen in it. Now, this is all at sea level. As soon as you start going way up, not only does the atmosphere actually get thinner and thinner, but the composition to some degree changes because of the buoyancy of these different gases. Something we don't really need to deal with or know, because essentially we're going to be dealing with these ideal gases. We're going to be dealing with pressures and systems that are generally on the Earth. We may be dealing with airplanes and stuff that kind of go up into the air, and at some point we may discuss maybe what the systems, what the pressure systems may be in, say, the International Space Station. But essentially, there's still pressurized air in there. So whenever we're down near the surface of the Earth, we're dealing with pressurized air, and generally that pressurized air is going to sit in this ratio here. It's going to be 78 to 21, and there are all these other little tiny things in between. But essentially, I just kind of need you to get an understanding of what this looks like. What's the stuff that we're breathing, that we're living in, that we actually take and compress and do mechanical work with. So right now I just want a little bit of history of what's going on here. The word pneuma, or pneumatics, matics, dynamics, kinematics, right? This is the study of motion. So essentially, pneuma is the word for the Greek word for the meaning of breath as well, and in some cases it's actually used for spirit, which is like the air or whatever. So pneuma is the Greek word or the definition of breath itself, and then we get into pneumatics. It's essentially pneumodynamics. It's the dynamics of air. Okay, so that's fine. So we'll go on here. I like the word pneumodynamics, and I think it's actually a better name than pneumatics, because I like the word dynamics, because it really talks about, we're studying the physics of air, or breath, pneuma, right? Okay, so we know it's a branch of science that deals with the transmission of energy using gas. Now, it's interesting. I'm just going to pause here for a second. Are we studying the transmission of energy? Well, yeah. What kind of energy? Actually, mechanical energy. Yeah, truly. Like, we're not going to be studying like levers and stuff, but you'll see that there's a parallel between some of the formulas that we're going to study and actually the lever formula. And some of the other mechanical type formulas can kind of be seen in pneumatics to some degree. It's pretty cool. We're actually transmitting mechanical power. So anywhere we're transmitting force through air, it's called pneumatics, because it's a dynamic of pneumo. So pneumodynamics. There you go. So essentially what's going on is that we need to talk about two kinds of air. I've already kind of talked about one kind of air. I've talked about the atmosphere. And I've said there's a particular kind of compartmentalization of that atmosphere where we have a certain amount of oxygen, a certain amount of nitrogen, a little argon, and a bunch of other things. Okay, so generally all of the air we're going to study is going to be like that. Now, if I wanted to, I could apply the same rules, the same laws, the same math, the same physics, everything we're going to talk about with any other gas. I could use like pure hydrogen, or, well, maybe I wouldn't want to deal with pure hydrogen, but certainly pure nitrogen or pure argon or any kind of inert gas, helium, stuff like that. So, but we're going to be generally dealing with pure pneumatic systems that are compressing air from the atmosphere. So as soon as we compress it, it turns from free air into compressed air. Free air is just this, right? It's just this stuff here. Right? That we're breathing it, we're interacting, we're walking through it. As I'm moving my hands like this, I can feel the air. As I'm doing that, that's called free air. As soon as we compress it and shove it in a tank and capture it in here and compress it in here, so put the density of the air in here, if it was compressed, would be greater than the density of air outside the tank. So I'm shoving more and more and more air in there. Actually, you know what? We can't make compressed air without an ideal gas, without that enclosed container. Okay, so as soon as we compress it, it's no longer free air. It's compressed air. Again, it's got to be an ideal gas. It's got to be inside a container. So, and it's denser. So the density of that air in that tank is greater than the density outside the tank. Actually, I'll tell you this, if you really think about it, the atmospheric prayer, that's an interesting one. The atmospheric air is pressurized. Does it make sense? I mean, think about it. The atmospheric air is pressurized. Okay, why is it pressurized? Well, hold on to that thought. Let's just continue a little bit here. So, okay, free air, okay, can actually be any temperature or any pressure and have any humidity and whatever. So we're going to talk about kind of not just free air and compressed air, but we're going to get into defining what compressed air is, and maybe there are different terms for compressed air. But right now, let's just talk about this air that's sitting here. Okay, so free air can be any temperature, any pressure, any humidity, whatever it is, it's called free air. Free air doesn't mean it's defined as anything. It doesn't have to be 21% oxygen and 78% nitrogen. It doesn't have to have a certain humidity. It doesn't have to have a certain pressure. It can be really low pressure. Actually, you could go up a mountain. You go way, way, way high on a mountain, and the air pressure up there is really low, but it's still free air. When we talk about standard air, we kind of have to put some values to it, because when we start to do the physics, right, because we're assuming we're going to put free air into this tank. Okay, I'm going to compress air and put it in here. I have to kind of have a ballpark number for my physics. So I'm going to start with what I call standard air. Now, standard air is just general, like if you get like really specific and you want, I need exactly standard air, then it has to be exactly 14.7 pounds per square inch. And it also has to be exactly 68%, 68 degrees or 20 degrees Celsius, and it has to be 36 degrees relative humidity. Exactly. So that's actually what standard air is. Okay, so standard air is free air that has a certain temperature, pressure, and certain humidity, and there are different types of standard air. But generally, we just call it STP, standard temperature and pressure. Okay, and that's when we're talking about generally the pressure that we're going to be dealing with pneumatics. Now, if you're in the desert and it's like you're down in Death Valley, well, it's not actually standard pressure, but generally you're going to still use the same formulas. If you're maybe, up in Alberta somewhere 1,000 feet up, you're going to use the same formulas. But it's not exactly standard air. And if it's in the winter or in the summer, it's not going to exactly be standard air. But generally, it's something that we talk about, saying this is the type of air we use when we're doing the math for compressing. If we get into really specialized situations, like if we go up in an airplane or way up the top of a mountain, then we're not dealing with standard air. And the formulas change a little bit, but generally they are still pretty much the same. But right now we're just going to say, hey, when we're talking about compressed air, we're talking about standard air. Okay, standard temperature and pressure, even though it's not exactly that, but we're just going to roll with that. Now, as far as, the compression of gas goes, and taking kind of a look at the history of this, we've got this cool concept of the bellows. I'm not sure if you've used a bellows, but I remember when I was a kid, we had one by the fireplace. And, you're actually kind of capturing the air inside and you're compressing it to some degree. It has a vent. It can come out, right? So we're actually creating pressurized air. Now, the pressurized air inside that bellow, as I'm squeezing it down, there's a little bit of back force from all of it going out the nozzle. So there is some pressure generated inside, but generally the air that's in there is still not considered kind of air that I'm compressing. So I'm not really dealing with an ideal gas, but we're talking about the history of pneumatics. At the beginning, blowguns, they go way, way, way back to like, I don't know how far they go back. But the bellow itself, it goes back hundreds and hundreds of years. So they weren't dealing actually with an ideal gas. It was pretty close. So in this situation, we are actually compressing air to some degree in here, but it's coming out of the nozzle. But that was really the first compressor that we can really think of. Now, if we go way back, we can say, well, blowguns were used way, way back when. They're compressing gas as well. Again, not dealing with an exact ideal gas, but still working with the ideas of pressurized gas. In this case, this is probably the first thing of like pure like mechanical transmission or pneumodynamics. Pretty cool, because you're making a projectile go, right? So there's definitely pneumodynamics going on here. So it was pretty cool, actually. It goes way back when to the late 1800s, where France installed this huge compressor. I think it had to do with the water system in France. So they were pressurizing the water system to make it go around. But one of the things I do know about, which is pretty cool, which I'll show you a picture of, was the first pneumatic drilling was used way back when. In Italy, when they were making this huge, I think it was a 12-kilometer tunnel. It goes way into the mountains. It's pretty cool. So what they did was, it was a gentleman who designed this pneumatic drill. And I'll show you a picture of it. Pretty cool, eh? So what's going on here is a bunch of guys here working on this drill, and they had all of these pneumatic drills that were going out. And you can see there's kind of the manifold here, and you had some pressurized gas coming in, and there's some tubes and some levers and stuff. And this looks pretty cool. What was going on here was, this was the first pneumatic drill that was actually drilling into rock. So it's an application. This is going way back. This is the late 1800s. So pneumatics or pneumodynamics, like actual pneumatic systems doing mechanical work for us, have been around for a long time. It's pretty cool just kind of going back to a little bit of the mechanical physics here. What they were doing is they were using waterfalls. Actually, it was a waterfall at either end of the tunnel. They were kind of boring both ways, but there was a waterfall at one end, and the water falling, actually, they used that to generate pressurized gas. So we're taking mechanical motion, turning it into kind of more potential mechanical motion and pressurizing gas, and then having that go move drills. So it's pretty cool. Ultimately, they were drilling the hole with water, but they were just transmitting the power, drilling this tunnel with the power of water, but they were transmitting the mechanical force through pressurized air, or pneumodynamics. Super cool. So let's take a look at this. I need you to think about an example. I'm going to get my pneumatic actuator over here. And I'd like to talk about this particular example, but I need you to kind of imagine something, because we're not in an actual classroom. But if we were, I think this might help a little bit. So we're going to talk about the transmission of power. Okay, in some cases when we have mechanical power, we actually have levers or belts or pulleys or whatever, cams and gears and stuff that are actually mechanically transmitting power from A to B. The same thing exists for electrical transmission, and we know that happens through a wire, some kind of conductor. Essentially, we're transmitting electrical energy or electrical power through a wire, and the conduit in this case is a wire. I guess the conduit in a mechanical system is an actual gear or shaft or pulley or whatever it is the device itself transmitting the mechanical power. Hydraulic systems, pretty cool, just like a pneumatic system, except for they use pressurized fluid as opposed to pressurized air. And what's going on in this situation is that we have a pneumatic actuator, and I'm going to show you an example of this. Hold on a second. I need you to look at this guy. Here's a pneumatic actuator, okay? So what's going on is that if I've got my hose over here, okay, I'm just going to grab this guy over here. I've got this hose. I'm not going to hook this up, but let's just imagine this. This is a hose. This is a floppy hose, whatever. I can put 100 PSI through here, whatever that means. And it's a cool hose. Now I've got my actuator over here. Now I need you to imagine this. There's a door over there. I want to make a mechanism that I can open and close that door. Not only can I open the door, but I can close the door. First thing that comes to mind, if I need the mechanical transmission from my hands, right? Maybe I could hook up a clothesline. I mean, I don't know if you've ever used a clothesline or not, but I mean, you pull it one way and it goes this way, and the other line goes that way. So there's this going on, and you can do this back and forth and back and forth. So I could put a pulley over there and a pulley over here, and somehow hook up maybe something, maybe a rod or something to the line that I could physically pull the door. And if I did this, I could push the door and I could close and open that door. I would be using tension on cables. Okay, well, I could do that. I mean, you could think of a bunch of other ways of mechanically moving that door. I mean, I'm talking about transmission of mechanical energy from here to there. I mean, I could put an electric motor over there and put the battery here, but let's just stick to the dynamics, the actual physical movement, the physics. I could put a shaft on there. Actually, I could put a cable on there and pull the door, but I wouldn't be able to push it. I could push it and pull it. Okay, so I could, if I put maybe a rod on, I could push and pull the rod. I would imagine you can think of a bunch of other things. I could have a shaft that I could turn, right? I could put a gearbox over there, and I could make the door move. Okay, so all of those are pretty complicated things. What about safety? Well, probably not a lot of force is going on there, but those, whatever that is, I've got to make sure it's up on the ceiling and it's out of the way of people and stuff, and I may have to like brace it. And especially actually if I'm using cables, I'd have to add some tensions in there, some tensioners or something. If I was using a shaft or a rod, especially to turn, I'd have to build a box over there with pulleys and stuff, and it would be pretty complicated, and bearings and stuff. Any kind of mechanical system that you would imagine building is going to be more complicated than if you were to just put this on the door, right? If I were to hook that up to the door and push and pull it, and then I would make this go in and out, what if I had two hoses? One hose hooked up to this side and one hose hooked up to this side. And I had some kind of maybe some kind of valve where I could switch the air to go down one hose or down the other hose. Well, what does the actual safety factor look like that? Well, essentially, how do I get that hose from here to there? I could just hang it on the ceiling. I mean, if I really wanted to, I could just put screws in the ceiling and kind of drape it along there. Maybe some tie straps. And guess what? That's kind of, it's the code. I mean, as far as like the safety code for running pneumatic hose, I don't think there is one. As long as it's just out of the way and you're smart enough that you're not going to hit it, block it with something. You know what? Even if it were to get broken, if you were to cut that hose, some air flies out, maybe you get a little hose whip or something like that. But if you put a tie strap on there, it's going to grab the hose whip, but it's not going to let the hose go flying all over the place. So it's pretty safe. As far as like the mechanism goes, it's not a lot of energy or work for me to actually design something. I mean, the most complicated thing is me to make a bracket that goes on here on the wall or somewhere that actually opens and closes the door. But pardon me, that doesn't even have to be that complicated. So what I'm saying is pneumatics is really cool. Like, think about how cool that is. I can actually transmit mechanical power from A to B with very little safety consideration. I mean, certainly I don't have to tie stuff down like I would, like with a bearing or a shaft or a pulley or some kind of gearbox or something like that. I mean, and what about accuracy? Well, I can still control that door really accurately, actually, with pneumatics. As long as there's no back force on the door, like a really heavy spring on the door. If it's pretty free-flowing, I can actually do motion control pretty accurately with that to some degree. I mean, if I wanted that degree of accuracy, I could also use a pulley or a shaft or a gear or whatever, but I'm saying it's comparable. It's really cool. It's safe, and like it doesn't cost me much to install it. And actually, in the end, it's probably going to last longer than any of those other pulleys or shafts or gears or whatever, because the accuracy and the counter forces and tensions and stuff that are in those mechanisms are actually going to be, there's going to be what we call backlash in the system. There's no backlash in a pneumatic system. And if there is backlash, and you guys may know that, especially if those who are studying mechanical engineering, the backlash is just kind of counter pressure. That's just a little kind of counter force, a little bit of pressure fluctuation in the system. Nothing. Pressure what I say about pneumatic systems is they're very forgivable. They can deal with backlash really very easily. So that's pretty cool. So pneumatics is really cool, and there's some application of kind of the difference between other mechanical power transmission and this pneumatics. Now, we could do the same thing with hydraulics, but hydraulics often work with really high pressures. And although they're much more accurate in their motion control, they are a little bit more dangerous. And when we're dealing with hydraulic systems, yes, there are more safety protocols on how to actually install the lines and the hoses and make sure that all the system is a lot more safe. And the types of lines are more expensive. With pneumatics, we can pretty much just use a garden hose. So actuators. We just talked about that actuator over there. You can imagine how it works. There's pressurized air that goes on the back, and depending on the area, that pressurized air is going to apply a certain amount of force. So it's going to create a certain amount of force depending on the area. So as long as whatever we're pushing against is not pushing back so much that the pressurized air that's creating the force is less than what it's pushing, or that is greater than whatever it's pushing at, something's going to move. Yeah, so the basic principle, I think, makes a lot of sense. Now, how do we measure this stuff? Well, lots of different kinds to measure this stuff. We can measure really accurately or non-accurately. When we get into the really small little types of electronic type measurement, we have things like this. These are little kind of electronic pressure sensors, okay? So essentially what's going on here is that there's a little diaphragm in here that gets pushed this way or that way against the atmospheric pressure here. And this is actually studying the differential between the atmospheric pressure and the pressure, say, coming out of this hose connected to a pressure vessel. The other thing is we can use a Borden gauge, which is pretty common type gauge. Here it is. I found the one that I ripped apart. So I'm actually gonna undo it for you. Just give me a sec. So these screws in the back, and there's a housing here. And you'll see it's actually pretty cool. And this, again, is a differential gauge. It's studying the difference between the atmosphere outside this and the atmosphere inside whatever this thing's hooked up to. Here we go. So if I take a look at this is pretty cool. Here's the gauge, right? Okay. There's this meter thing that spins. And then watch this. Essentially, what's going on is that this is an NPT thread, National Pipe Thread. We'll talk about NPTs a little bit later. So this is put inside a vessel. So that air pig that I had, this air vessel here, you can see there's a Borden gauge on here as well. Okay, so that gauge goes up to probably 120. What does it go up to? It goes up to 160, but you can see there's kind of a red zone at 125. Generally, when we're talking about compressed air, when we're doing work with the compressed air, mechanical power transmission, just general stuff, we're going to deal with pressures under 120 psi. This is really cool. Let me flip this thing around. Take a look at that. What's going on there is that there's a certain amount of force from the atmosphere that's pushing on this thing. Now, the outside of this has a greater surface area than the inside. It's interesting to note that the inside, if I were to put pressurized air in here, by the way, that's an empty tube. This tube is empty inside. The area inside this tube and the walls of the inside of the tube is less than the area outside the tube. So essentially what's going on is that if I were to put pressurized air in here, in this little tube, what it's going to do is it's going to create these forces. Now, the area on the inside is less than the area on the outside. So what's actually going to happen is that when I actually have pressurized air on the inside here, on the inside of this tube, what I say is the area, I guess, on the outside of this bend and the area on the inside of the bend is different, or the length is a little bit different. So what's going on is that when I put pressurized air inside this tube, that's an empty tube, it's just a flat, thin tube. When I put pressurized air in there, what happens actually, is pretty cool, is that the forces on either side are different. And what happens is this thing actually starts to expand. And when it expands, look what happens. When that expands, that goes up. Pretty cool, eh? Yeah. So when that expands, this physically deforms. It's kind of like a bimetallic strip in a temperature sensor, in a temperature switch. Very similar to that. So what's going on is that depending on the differential between the force of the air pushing on this side, and the force of the air on the inside that's pressing, this thing is going to deform or bend to some degree, and then it changes. Bourdon gauges. These can actually get very accurate, up to 0.1 psi, whatever a psi is. Yes, we are definitely going to talk about how to measure different kinds of units of measuring pressurized air. But bear with me. This is a pretty cool concept. So that's a Bourdon gauge. Very, very common type gauge that you'll see all over the place. These are everywhere in pneumatic systems. I don't think you'll have a pneumatic system that does not have one of these on it. It'd be pretty rare. I've never seen one. The other thing is that when we have a really high pressurized system, like 5,000 psi, you know those jackhammers you see in the street sometime? Or maybe those really, really big compressors that sit behind trucks on construction sites and stuff that run really high pressurized systems. Actually, I have a friend of mine, and he works in irrigation. And what they do is they put irrigation lines underneath the ground. He does golf courses, stuff like that. So in the winter, what they have to do is, before the winter flies, they've got to pressurize the lines and force all of the air out. So these really high pressure with really high flow. When you're dealing with pressures like over 1,000 psi and even greater, up to like 5,000 psi, you're going to use a plunger gauge. So plunger gauges can deal with much high pressures, 500 to 5,000 psi G. Now, when I say G in psi, I'll get to that. Just bear with me. There's actually kind of a difference, but there kind of isn't. Let's just roll with this. When we're dealing with Bourdon gauges, usually they're under 500 psi. When we're dealing with over 500 psi, we're dealing with a plunger gauge. Plunger gauges can't sense. If you were to look at a plunger gauge and the pressure changed 2 or 3 psi, you wouldn't see it move because the scale is so big. It's kind of like, you know, can you see the minutes of an hour go by on the hour hand going from one to the other? No, but you can certainly see the seconds go by and then the minutes go by slowly. You can actually watch a minute hand. You can see it if it's in a big clock. But what I'm saying is that Bourdon gauges are much more accurate at seeing really low pressures changes, differential pressure changes. But the plunger gauges are dealing with really high psi. So you might see a change of 100 psi in a plunger gauge, but certainly you wouldn't see a change of 10. Okay, cool. So let's go on to talk about a little bit about a formulation. This is our first formula that we're going to jump into. After this, we're going to jump into kind of taking a look at different kinds of pressures and how we define what pressure is. Okay, for here, we're going to deal with this fact that the force is the pressure times the area. We've talked about that when we studied Introduction to Controls together, where voltage and pressure are synonymous. And you know pressure is measured in PSI, pounds per square inch. There are lots of other ways that we can measure it, but you may know pressure in a garden hose. You've dealt with water coming out of a garden hose. You've kind of felt the water coming out and you understand the pressure. That type of concept there can be used in pneumatics as well, because we're dealing with fluid power. Pneumatics is a study of fluid power. So we're dealing with the fluid, with the power of fluids. And yes, actually we consider air moving in a tube actually a fluid. It's pretty cool. Even though it's not doesn't have the properties of a fluid, we still call it a fluid because it's fluid power. Okay, let's continue on. So essentially what's going on is there are lots of different ways to measure pressure. We're going to stick with pounds per square inch because we're dealing with the American industry where in your career, you're also most likely going to deal with metric parts. Like if you go with SMC, SMC is a manufacturer who manufactures all kinds of pneumatic components, and they use metric. We're going to be dealing with PSI because most of the systems we're going to be working on are adopted from technologies from the United States, so it's all in PSI. But we also have, for force, we've got pounds and area square inches. Of course, you know force in SI. The System International is in newtons, and the area for SI is meters squared. So if you come across that, you have to just make note. Okay, you're going to have to do some conversions because even though the math all works the same, we're just going to go through the math using imperial units. So let's continue talking about pressure. Essentially, we're going to talk about three kinds of pressure. The first is going to be atmospheric pressure, and then we'll talk about a couple other different ways of measuring pressure. But essentially, what we're dealing with is an ideal gas to some degree. Not really, but I mean, it is an enclosed space. Think about it. I mean, the atmosphere itself, it's an enclosed space. It's not quite as enclosed as, say, a pressure tank, but it is kind of enclosed. And the thing I'm trying to get to is the fact that the atmosphere is pressurized. I mean, you've heard of something called atmospheric pressure. Yeah, so it's obviously pressurized. So the atmosphere itself is this kind of heavyweight gas that's coming down, and gravity actually makes it kind of, press down. Very much like water. If you're at the bottom of a pool, I mean, you can feel the pressure there. So the weight of the atmosphere itself increases. I mean, increases the pressure. And as we know, that as we go from space down towards Earth, the density of the air increases as well. So what's going on here is it's very much like if you go down at the bottom of a pool. As you go deeper and deeper and deeper, the pressure increases. Now, this is really cool. I want to start with this really cool concept, and it's this. The reason that we deal with the reason the pressure exists, or another way of actually looking at it, is this. If you were to take a column of air that was 1 inch by 1 inch and take it all the way from sea level all the way up to the edge of space, the very edge, like as far as you can go, way out in the exosphere, way, way, way out there. And if you were to take all that air and say compress it into right, stick it into a cube, and measure it, or somehow put it on a scale, it would weigh 14.7 pounds. It's pretty cool. And that's why the atmospheric pressure is 14.7 pounds per square inch. Actually, it's because if you were to take a column of air, 1 square inch, and go all the way up to the atmosphere and measure all that air, it would be 14.7 pounds. So cool, eh? So now we're experts on atmospheric pressure. You get it. I mean, there's that pressure that exists. It's like being at the bottom of a pool. You feel that in your ears. If you've ever divin down, because that's a word. If you ever dove down deep into a lake or a pool, you feel that pressure. And the deeper you go, the pressure goes. And if you go down to the bottom of the sea, it's like ridiculously high pressure. It's because of the weight of all of the water above. The atmosphere pressure, it's the same. Now, what I want to do is I want to get into two different ways of kind of measuring pressure. Whatever the pressure is, whether we're measuring the pressure of the atmosphere or measuring the pressure inside an air pig or a tank or whatever it is, that red tank that I have here beside me. Just essentially what's going on is that we've got two ways of measuring air. One is called absolute pressure. And the other is called gauge pressure. Gauge pressure comes from a gauge, like a Borden gauge. Gauge pressure is a differential pressure. It's the difference between the atmosphere outside the enclosed vessel, outside that ideal gas, and the inside, which is the ideal gas itself. So that pressure inside, say, a tube, or on a motorcycle, or a bicycle, or a basketball, or doesn't matter. Air mattress. You have pressurized air before. I don't know if anybody's blown up an air mattress, but I'm sure you've blown up a bicycle or something. You understand that you're just shoving air in there. You're just adding more and more and more and more air in there. You're actually taking atmospheric air that's already at a certain pressure. Right? You understand that? And you're shoving it into an enclosed area and you're increasing the pressure. Okay, well, how do we measure that pressure? Well, we measure the gauge. Is the pressure, I mean, the answer is yes. Is the pressure inside different than the pressure outside? Well, if we're shoving it in, yes. But the thing is the pressure outside the pressurized tank or outside the pressurized ball or outside the pressurized tire, is that air outside zero? Well, zero what? It's all relative, right? So I'm trying to highlight the fact that it's all air pressure is all relative. So we have kinds of two ways of measuring air pressure. It doesn't matter what we're measuring. You can measure anything in both ways of measuring air pressure. One is called gauge pressure and the other is absolute pressure. That's it. There are only two ways of measuring pressure. That's it. Oh, goodbye. Wait. Let's take a look at an example. If I really wanted to, I could say, okay, the atmospheric pressure is 14.7 pounds per square inch. What's that relative to? I just told you, all pressure is relative to something. Okay, so what's it relative to? Space. Relative to nothing. It's relative to not the atmosphere, right? So what's the pressure at the bottom of the pool at the bottom of the pool? Well, it's certain pressure. What's the pressure what's the water pressure 2 feet above the pool? No. Right? So what I'm saying is that when we go way out into space, way outside the atmosphere, what's the pressure there? Well, it could be zero, I think, yeah? Zero what? Okay, let's just go with PSI. 0 pounds per square inch. You know, I'm down with that. I think you're down with that. That's not complicated. Yep, we're good. As you go down further into the atmosphere, the pressure increases until you get down to 14.7 pounds per square inch. Okay, can we call that like maybe absolute pressure? Like absolute pressure relative to space. So it's relative to space. It's relative to nothing. It's the absolute pressure. Okay, here we go. I'm gonna pick up my tank. Right now, there's no pressurized air in this tank. It's actually it's called an empty tank. Although there's air in here, but the air in here is atmospheric air. What's the pressure of the air in here? Well, it's the same as the pressure of the atmosphere. So it's 14.7 psi. Well, yeah, but you know what? I did say that this 14.7 psi, pounds per square inch, is absolute pressure. So I'm going to say that the pressure of the atmosphere is 14.7 psi A. It's an acronym. Pounds per square inch atmosphere, or pounds per square inch absolute. Again, I just told you there are two ways to measure pressure. One is absolute pressure and the other is gauge pressure. Okay, so this gauge pressure is differential. It's comparing the difference between the pressure inside a vessel and the pressure of the atmosphere. It's the difference between the two. Absolute pressure is the difference between whatever pressure you're studying and space. Now, the air in here, as we know, it's 14.7 psi A. What if I were to put 1 psi in here? If I were to hook up my compressor, okay, and put air in here until that gauge read 1 psi. That gauge is going to read 1 psi G. We call this psi G for gauge pressure, right? That is telling me that the air in here is 1 psi G more than the air outside the tank, and the air outside the tank is 14.7 psi A. So what's the pressure in here A? What's the absolute pressure in here if the gauge pressure is 1? It's not complicated. It's 15.7 psi. Okay, so what I'm saying is that we can measure pressure in either gauge pressure or absolute pressure. You can measure the pressurized air in a tank. If the pressurized air in here was 100 psi G, the atmospheric pressure in here would be 114.7 psi A. So relative to space, the pressure in there, if it was at 100 psi G, would be 114.7 psi A relative to atmosphere. Again, all pressure is relative. All pressure readings are relative. Gauge pressure is how much more the pressure is than the pressure in the atmosphere. Absolute pressure is how much more any pressurized system is, whether it's in a tank or in the atmosphere. It doesn't matter. How much more it is than no pressure. Vacuum, space, right? Okay, so now let me ask you a really cool question. If I were, now this is a little crazy, okay? If I were to seal this tank, okay? Now, there's no pressure in it, okay? But if I got 14.7 psi A in here, okay? It's open to atmosphere right now, it is. If I were to close it to atmosphere and have this gauge, right? If I were to close it to atmosphere, right now, that gauge doesn't say anything. If I were to close this up, and then I started taking it up a mountain, higher and higher and higher and higher up on the mountain. Think about this. This is actually really important that you understand this, because this question is on the exam. Did I just say that? Yeah. Okay, here we go. You really got to wrap your head around this. This Borden gauge on this tank is a differential meter. Right now, on the ground, I take this tank, it says 0 psi. So therefore, the pressure in here is 14.7 psi A relative to space. If I were to take this and seal it and then take it up a mountain, higher and higher, took up an airplane, higher and higher and higher and higher. It's on the outside of an airplane. That gauge would start going up, would start reading a higher pressure because it's a differential gauge. The pressure in here is 14.7 psi A. Doesn't matter. As long as I seal it, it's always 14.7 psi A. But the gauge pressure being relative to the pressure of the atmosphere around it will change if the atmosphere around it changed. If I were to shove this into space, well, then this gauge would read 14.7 psi G. Really would. It really would. Because the atmospheric pressure is 14.7 psi A down at the bottom of the atmosphere. It's 14.7 psi more than the air around it. This is a differential gauge. It tells me the difference between the two. If I were to take that tank and throw it into space, that would no longer read 0. It would read 14.7 psi. It would. Pretty cool, eh? So what's going on is that pressure is studied in two things. One is gauge pressure, which is relative to the pressure inside a vessel and the pressure outside a vessel. It's the difference between the two. Or it's absolute pressure. Now the thing is, my gauge pressure, as we know, is going to change depending on if I'm on an airplane going up and down, or depending on if I'm going up or down a mountain, if I'm going down a Death Valley way down below sea level, whatever it is, it's going to change a little bit, but the absolute pressure is going to stay the same. It's always going to stay. Relative to space is not going to change. Okay, good. So what I want to do is, this is absolute pressure. So that I should have jumped to this slide earlier. So essentially, it's relative to perfect vacuum in space, and that's that. Okay, absolute pressure. So we use these situations, we're talking about flow characteristics for filters. And because the flow characteristic of a filter, it has to be studied in absolute pressure, because I'm going to study the pressure on one side and the pressure on the other side. If there's atmospheric differences, I'm going to get different rates, different flow rates, different pressures on either side, and they may not be consistent. So for flow dynamics, often we're using absolute pressure to study pressures on either side. And when we're dealing with back pressure for flow analysis and measuring leaks and blockages and stuff, we deal with absolute pressures as well, because again, if the pressure outside a system is different on one side of the filter on the other, or one side of a tank or the other side of the tank, or one side of a line and the other side of a line, like if I were to study the pressure differential on a line that went up and down over a mountain, up and down, I'm going to study absolute pressure. If I deal with gauge pressure, I'm going to be dealing with the pressures in the atmosphere on a mountain and the pressure in the atmosphere in the prairie. It's going to be different. So when we really want to deal with very accurate type measurements, we deal with absolute pressure, especially when we're dealing with really low pressures. Like if I were to study the pressure of the atmosphere up a mountain, or the pressure of the atmosphere down on the sea level, well, I'm dealing with absolute pressure no matter what. So absolute pressure is important for really accurate measurements. And we deal with it in airplanes, spaceships, measuring vacuum systems. When we get into vacuums, we'll get deep into vacuums in the final weeks of this course. And any kind of vessels, studying the dynamics of things changing, we are going to be studying absolute pressure. Now, this is kind of a cool example, essentially. This bag of chips was manufactured on the ground, okay? So, and there's a certain amount of air inside, and that air is actually atmospheric pressure. I mean, they might have actually pressurized the bag a little bit when they sealed it, but because it's not actually bloating, it's not pressurized air in there. It's actually 14.7 psi inside the bag of chips. Now, again, the gauge pressure is 0 inside the bag of chips. As soon as we take the chips on an airplane, because the pressure in the airplane is decreasing. So what's going on here? Ever take a bag of chips on an airplane? If you haven't, dude, do it. It's so cool. Yeah, buy a bag of chips before you get to the airplane, take it, and it'll pop up. You have to do that because it's so cool. Okay, good. So what's going on here is that, so if you ever take a bag of chips, did the pressure inside the bag increase? Did this around question? Remember I said there are two kinds of pressure. There's absolute pressure and gauge pressure. What is the question? Okay, let's just do this. Two questions here. Did the pressure of the bag inside relative to the cabin air increase? Yes, it did. Did the pressure of the bag change relative to the space? No, didn't. Right? So essentially what's going on is that, again, just going back to the concept of when we're measuring pressure, it's relative to something. Gauge pressure is relative to what atmosphere we're existing in. And then also any kind of pressure that's absolute pressure relative to vacuum or space. So here we go. Here's some formulas. I think you could have derived this formula yourself. So gauge pressure, essentially, and atmospheric pressure and absolute pressure are all kind of linked to each other. And we know the atmospheric pressure changes to some degree. So the gauge pressure will also fluctuate depending on what the atmospheric pressure is, which we just talked about, taking my tank up a mountain or into space. But there's a formula where we can put them all together. And we can say that absolute pressure is gauge pressure plus atmospheric pressure. Okay, there you go. So, and then as soon as we go below this value, we get into something called a vacuum pressure, which is so really cool. But below, once we go below atmospheric pressure, we get into vacuum pressures, which we'll study in-depthly later on. So here's some pretty cool measurements or whatever, but this is where I get into the acronyms. Now, when we're measuring things in absolute pressure, like when we measure the atmosphere, or when we measure the pressures on either side of filter, when we're dealing with flow rates through filters and stuff, or we're doing very accurate scientific measurements or measurements of really low pressures, we're going to measure it in PSIA. We're going to use the acronym PSIA. Okay, because we're measuring absolute. Now, again, it's an acronym, not a unit. I'm about to do some math without units, which is a little weird, but this is for you to practice wrapping your head around understanding the three kinds of pressures that you'll be dealing with and talking about: atmospheric, gauge, and absolute. So, what's going on is that atmospheric pressure is measured in absolute. Gauge pressure is measured in PSIG. Or we can actually say a PSI. So whenever absolutely, for sure, you're dealing with absolute pressure, you use PSIA. Anytime you're talking about gauge pressure, you use PSI. If you like, you can say PSIG too. But the only thing is, again, there are two types of measurement. One is absolute pressure, the other is gauge pressure. The acronym for absolute pressure is PSIA. The acronym for gauge pressure is PSI or PSIG. Either or is fine. So if you just see something that says PSI, essentially you know it's PSIG. And by the way, almost all of the formulations we're going to do are in PSIG. Unless we get into a little bit of the gas laws, which is something else when we get into like the physics of things. But essentially, if I have my pneumatic actuator over here and I want to, study how much force is being generated, I'm going to use the pressure of the compressor, which is actually the gauge, whatever the gauge says on the pressure, which is PSIG. But I'm just going to write it as PSI. Or if I'm going to label one of my systems, And if I know that it's at 100 psi, I just can write psi. But it's understood that we're reading a gauge. If you write PSI-A, it's specific to PSI-A. Here's a bunch of things here, acronyms that you can kind of wrap your head around for the understanding of all of these. Let's just look at an example over here. So we're going to do a little bit of math, okay? So what we've got is the same situation. We are calculating gauge pressure, absolute pressure, and then we're going to calculate atmospheric pressure with the same situation. So I've got a tank here. I want to know what the absolute pressure is. So I want to know what the pressure in here relative to space, okay? I want to know what it is in there. But all I have is gauge pressure, right? There's no absolute pressure gauge, although you can get absolute pressure, not gauges, you can get absolute pressure readers. Right now I don't have one. I just have to calculate it. I've got this, and I know what the atmospheric pressure is. Somebody told me the atmospheric pressure. Atmospheric pressure is 14.69 psi-A, because we measure the atmosphere in absolute, because we're measuring it relative to space. We also know that there's a gauge that says 10 psi, so that's relative to the atmospheric pressure. It's at 10 more than the atmospheric pressure. So what's the absolute pressure? Well, that's easy. Just do the math. Now watch this. I mean, this is simple math, but it's important to look at the acronyms. Again, in this case, we're dealing with absolute pressure. Sorry, I wrote that. I was just editing this earlier. I'm going to take that out. PSI. Okay, good. So I'm dealing with 10 PSI. I'm actually glad I did that just to highlight the fact that that is PSI because it's gauge pressure, right? Okay, it's not absolute pressure. It doesn't have that A there. So what's going on is that I know the acronyms, they're okay. Essentially, we're still using the same units, pounds per square inch plus pounds per square inch, same units. But in this case, we're kind of adding with acronyms, which generally, this is the only time I want you to do that. I always want you to use units. But again, I'm talking with the acronyms so you can wrap your head around the difference between PSI and PSI-A and why it's important. So in this case, my absolute pressure, PSI sub A, okay, is going to be 24.69 PSI-A because we're dealing with absolute pressure. Okay, so I'm adding 10 PSI plus this. Now, it's the exact same situation. We're looking at it from a different perspective. I wanted to know what the absolute pressure was. In this situation, I want to know what the gauge pressure is. Let's say my gauge is broken. And I don't know what it is, okay? But somebody told me that the absolute pressure in this tank was 14.69 psi-A. Someone also told me that the pressure of the atmosphere was exactly 14.69 psi-A. I could do the math to calculate what the gauge pressure is in there because it's just the difference between the two. So I'm going to rearrange my formula. For my unknown, throw my values in. Again, PSI, PSI. In this case, the answer is PSI-A and PSI-A, and the answer is in PSI because I'm looking for gauge pressure. Again, we started with 10 PSI in the previous example, and we know that it's going to be the same. In this example, we're looking for atmospheric pressure. Let's say I didn't know what the atmospheric pressure was. But I knew the absolute pressure in the tank. Someone just told me what it was. And I knew what the gauge said, right? So this thing gives me the difference between the pressure inside and the pressure outside. Okay, I'm looking for the pressure outside. I know what the absolute pressure is inside, and I know what this tells me. Well, there's a formula that I can find the difference, or I can find the pressure outside. Well, it's just rearranging the formula. So my absolute pressure is measured in PSI-A, and this is PSI. Now again, I've always told you guys, always do math with the units. In this case, you may be thinking, well, they're different units, so how can we add them? Dude, these are not units. These are acronyms, and I'm getting you guys to do this to get used to these acronyms. Essentially, all of this is in pounds per square inch, so it's the same unit. We can do this. I just need you to understand the acronyms. It's a good example here because it tells you about really what atmosphere is really doing and what atmospheric pressure is really all about. Okay, so in this situation, there's this airport way, way, way up in Tibet, way up high in Tibet, and it's 14,000 feet. It's the highest airport on the planet. Okay, so what's going on there is that, let's just say in the maintenance bay, the airport, there's a compressor, okay, and with a reservoir tank. So you've probably seen a compressor. Actually, on this next slide, there's a tank in here, okay. So what's going on is that there's a meter on the tank, and the meter shows 80 psi, okay. 80 psi G. 80 psi. That's what it shows. Now, also, there's another gauge there that reads another meter that reads absolute pressure. So you can just use the math to calculate the difference, and now you can find that the atmospheric pressure, way up 14,000 feet, is actually, dude, it's so small. Right, compare that to like what you're used to living at, 14.7 psi. It's almost hard to imagine, but yeah, like people breathe and live and work up there. It's actually quite remarkable that they actually do that. But so you could probably feel the difference waving your hand. Now to end this, okay, we're done. I just need to stick with you. Need to stick with me. I'm not kidding. We've been talking about mechanical power. Mechanical power is this thing that's pushing some other thing, but we're talking about air. I need you to do this. No kidding. Like if you don't do this, like I do this in lecture, and then half my students do this, and the other half don't do it, and I just call them lame. Like, yeah, you know, you're not cool. You're not doing this. Dude, can you? I mean, you've done this before, but feel it, dude. There's a physical sensation there. There's stuff here. Air's really cool. It's stuff. Yeah, I need you to forget about the fact that you're just walking around in space. No, dude, you're walking around in air. Yeah, we're going to compress the air. We're going to do a lot of really cool things with compressed air as we go. Next week, we're going to be talking about actuators. We're going to talk about compressed air in actuators. And that's all. See you next week. Okay, bye.